Can we draw the products to these reactions? This is a general class of certain type of reaction called electrophilic addition. Double bonds are electron rich. Something like the HCl is going to be somewhat polarized, and these double bonds really want to reach out and grab that. We're going to look at that in detail. I'm going to just go ahead and write the products. So there would be our products. So here's a hydrogen, and now this thing has an extra one, and for some reason there's a hydrogen drawn there. Of course there's two here, so we might think of these as going across the double bond. On to reactions of alkenes. The double bond is the functional group. It has known chemistry. Like I said, it's electron rich, and so we're going to look at what we might call addition type reactions. And here we see hydrogen being added across the double bond. For catalysts like palladium and platinum, this looks like an endothermic reaction, true or false. You're breaking my thermodynamic heart. It's exothermic. Energy is a product. Remember Zeta's rule, and we'll remember when we go over the quiz, some alkenes might have a higher or lower heat of hydrogenation. Alright, the most common reaction of double bond transformation, the pi bond into a sigma bond. There's a pi bond. Of course, we like to think of a pi and a sigma and call it a double bond. Now it's just a single bond. So here's what I've warmed you up for. An addition reaction. Something adds across the double bond. And in the previous chapter, we went over this quite a little bit. How do we make an alkene? Dehydrohalogenation. If Y was a hydrogen, this would be dehydrohalogenation. And now we're all experts on substitution. So here is how we like to think of a pi bond having electron density above and below the molecule. An sp2 hybrid carbons, flat and planar. You can tell me the bond angles and all that good stuff. So we say the double bond acts as a nucleophile, attacking electrophiles. Carbocations are the intermediate, so here's the electrophile, the double bonds jump onto that, and then it breaks this pi bond, and there is a carbocation, and we call these electrophilic additions. Here's kind of a very generic mechanism. Pi bonds attack the electrophile, carbocation gets formed, and then something else can act as a nucleophile, hitting the carbocation, and now we see we've added two atoms perhaps across a double bond. So just as with the substitution reactions, there was a whole variety of things we could make when we substituted something in for the leaving group. Here are a bunch of different addition reactions. Like hydration, we can add water across the double bond. So here's just what we're adding, not necessarily the reagents. If I put the hydronium ion here, we pretty much have the reagent. It's acid catalyzed. So here's an alcohol. We can turn an alkene into an alkane. We can make this thing called a diol. This starts out as an addition, turns into a cleavage, oxidative cleavage, epoxidation, halogenation, halohydrin formation. And here was our warm-up question on the whiteboard. We added HCl across a double bond. We may or may not get into this semester. Carbene addition. So hydrogen chloride, hydrogen bromide are going to be our common species to add to an alkene. First step, protonation of the double bond. Protonation step forms the most stable carbocation possible. Carbocation stability is a big thing. If you memorize that, that'll be a good foundation for a lot of answers and things working out correctly. Step 2, the nucleophile attacks the carbocation, forming an alkyl halide. HBr, HCl, and HI can be added through this reaction. Well, they chose a boring alkene here. 2-butene, protonation of the double bond, form a carbocation, and then bromide acts as a nucleophile, attacks there. So there's one way to make an alkyl halide, is to start out with an alkene and add a hydrogen bromide to this thing. How many of you like new big words? Here's our new big word, regioselectivity. What is regioselectivity? Markovnikov was a Russian, and he observed that the addition of a proton to a double bond of an alkene results in a product with the acidic proton bonded to the carbon atom that already holds the greater number of hydrogens. And so I like the rule, the rich get richer, which is why it's funny that Markovnikov was Russian. Because then I like to talk about Animal Farm, and that all animals are equal, but some animals are more equal than others. Rich get richer. What is the basis behind Markovnikov's rule? In electrophilic addition to the alkene, the electrophile adds in such a way that it generates the most stable intermediate. And what is the intermediate? Right, a carbocation. Carbocation stability. So this looks very similar to what's on the whiteboard. We'll throw the whiteboard up there in a second. This hydrogen could go to this carbon, or it could go to that carbon. And when I add it to, notice this carbon has no hydrogens. This carbon has a hydrogen. So this carbon is richer than this. And so this is the rich carbon, and it's going to get richer. Grabs this proton, forms this carbocation, and notice it's tertiary. If we try and give this would be a more equitable thing, share the wealth. This carbon's poor, this one's rich. Let's give the poor carbon the hydrogen, so they each have one, and we form a secondary carbocation. So nature wants to form the most stable carbocation, and that is the basis of Markovnikov's rule, and that tells us where to add the hydrogen. So that's the first step. Then the second step, bromine hits, and there you have your product. So over here, this carbon already has a hydrogen, so we're going to put the hydrogen there, and the halide's going to end up over there. So halide goes there, the other hydrogen goes there. This one here, that's why we drew that hydrogen in. This carbon has no hydrogens. So it gets the halide, and there we've added a second hydrogen. So we knew where to put these due to Markovnikov's rule. And we say this is regioselectivity. We know where these species are going to go. So here's an energy diagram. If it wasn't for the slide saying this, I would say we just get the Markovnikov product. So here's an alkene. Here's the richer carbon. This would be a wrong answer. So here's a secondary carbocation, and here's a tertiary carbocation. And so here's the product that is formed. And this reason for carbocation stability might be that alkyl groups, through induction, are electron donating. So this charge here on this carbon, there's this alkyl group, that alkyl group, and that alkyl group. Stabilize this by induction, where right here we only have this alkyl group and this alkyl group. So that might be why a secondary carbocation isn't as stable as a tertiary. What do you know about radical stability? Is it the same as cation stability or opposite? That'd be a good true and false question. They are the same. You got the true and false question. Anion, we're not talking about ions, radicals.
Well, that's the opposite.
Yeah, absolutely. So if most of our addition reactions are going to have the regioselectivity of Markovnikov regioselectivity. However, with HBr, it's really convenient to have it come out anti-Markovnikov stability if we just go down a different path, and that's the free radical addition. And we use a peroxide to form a free radical. So in the presence of peroxide, HBr adds to an alkene to form the anti-Markovnikov product. So we use peroxides to form the radicals. This doesn't work with HCl or HI. We only see this with HBr. And here's some boring thermodynamic stuff to explain why that is. So here is a peroxide. Now you've probably heard of hydrogen peroxide, H2O2. And it's very similar than what we have here. Here instead of H's we have R's. And a little bit of heat, this bond cleaves homolytically, so we form these two radicals, and then this radical encounters an HBr, and there's our half arrows, and then get another half arrow going, which forms a bromine radical. Now once we have a bromine radical, that's where we want to start our addition reaction. So bromine's what is added first and we form an alkyl radical, that's going to be the rate determining step. And so it's the same game as carbocation formation. We want to form the most stable alkyl radical. And the more substituted the radical is, the more stable it is. So we have a primary carbon and a secondary carbon, and if we put the radical on the secondary carbon, that means bromine adds here, and then once we have this radical, extract a hydrogen, forming another radical. Here's our product that has anti-Markovnikov regioselectivity. Markovnikov, we put the bromine here and the hydrogen here. Anti-Markovnikov, poor carbon gets a little richer. This rich one didn't get any richer. It still has its two hydrogens. Anti-Markovnikov regioselectivity. So the hydrogen's going to end up there. We don't want to form a secondary radical. Nature can form a tertiary radical. So let's draw the product to these two reactions. Let me just try and make a little mechanism out of this. And then, of course, bromide. There's like almost the complete mechanism. And here we had a CH2, and here we have a CH3. So the rich got richer. Here's your Markovnikov regioselectivity. Now down here, looks almost the same, except for this thing here. What is this? Yeah, it's an organic peroxide. R is our alkyl group, generic alkyl group. So when you see this, you want to think a free radical mechanism. And now I don't have room to write my intermediate. Half arrow, half arrow. Here's going to be my intermediate. And then some more HBr. So here's our Markovnikov regioselectivity. Here is our anti-Markovnikov regioselectivity. Any questions? You feel like adjourning early.